today we start the next section, so it will be part 3.1, and here we will talk about cosets. So, if you wish, in the next several sections we will discuss very fundamental ideas about groups, so ideas related to homomorphisms, cosets, kernels, and so on. So it is very standard stuff, you can find it in any textbook on group theory, and so after we discuss for a few lectures these very general ideas, we will start looking in more interesting concrete examples of groups related to geometry, number theory, and so on. Okay, so let me start with discussing cosets. And actually we have already seen a special case of this story when we discussed order of one element in Lagrange theorem. So let's suppose we are in the following situation. So let G be some group and H be a subgroup of G. So then we can just draw this situation by picturing H sitting inside G, and we can look at all other elements. And the idea is that we can take some element here, let me denote it by G, and then we can use elements in H to shift it around. We can multiply it on all elements in H. So this is G times identity, which is also in H, and we can move it to some element GH1, GH2, and so on. And then we will get a collection of elements in G, which are basically this element G shifted by all elements of H. By shifted, I mean multiplied from the right. And then I can take some other element, I don't know, G prime, and start multiplying it on all elements of H again, and so on. And I get another kind of class of elements, which is this G prime shifted by all elements of H, and so on. And so I can partition in this way my group. And these classes are called cosets. Cosets. And of course, in a second I will define a certain equivalence relation, and this will be classes of equivalence. So we have already seen this situation when we looked at a group and an element. So remember, when we had this element X inside the group G, we started to multiply all elements on X, and we got this collection of cycles. And our group was a union of cycles, where cycles represent the way, basically, what happens to an element when you multiply by X. And this is exactly the same picture. So in this case, you just should think about a subgroup generated by X inside G, and then these cycles in this graph will be literally these cosets. Okay, so it's obvious, right? Because you take some element G, and all elements here will be G, Gx, Gx squared. So you just multiply it on all powers of X, so all elements in the subgroup. So let me formally define that. And here there is a little interesting thing happening. So there are actually two definitions, left cosets and right cosets, and the reason is group is non-commutative. So you can multiply from right, you can multiply from left. So let me first define left cosets, and right cosets are of course very similar. So H is a subgroup of G. So then we have an equivalence relation on G, and equivalence relation is as follows. So I say that G1 is equivalent to G2 if, and then what I want them to be in the same coset, and being in the same coset means that basically G2 inverse G1 if and only if G2 inverse G1 is inside H. So what it means that if two of these elements coincide, and this is G1, this is G2. What it means that if you take G2 inverse multiply on G1, you will get an element of your subgroup. And then the claim is that this is an equivalence relation. So classes are called left cosets. And probably notation will be so set of left cosets is usually denoted by GH. Okay, so why it is an equivalence relation? So there are two ways to proceed. I can either leave it as an exercise or I can do it. So maybe let me do it. So remember, there are three things to check. So three things to check. And three things to check are the fact that it is every element is so G is equivalent to G, and the reason is of course because G inverse G is identity is inside H. And then, so G1 is equivalent to G2, implies that G2 inverse G1 is in H, but then you can always take an inverse in H, so it means that G1 inverse G2, which is G2 inverse G1 inverse is inside H, but this implies that G2 is equivalent to G1. And finally, you assume that G1 is equivalent to G2, G2 is equivalent to G3, and of course this implies that, okay, G1 inverse G2 inverse G1 is in H, and G3 inverse G2 is in H, and we just multiply. So this is a subgroup, so we can multiply, and we get G3 inverse G1 is in H, so G1 is equivalent to G3, and this is called transitivity. So here I just proved that this equivalence is an equivalence relation, and so indeed I can partition my group into this conjugacy classes. And then I need a name for it. So the name, if I take a class where my element G lies, so the convenient notation is to denote it by GH. And the reason is very simple, because it just all elements of G times H. So this is easy to check, that if I take elements equivalent to G, what I need to do to G1, say, I need to find elements so that if I multiply on G2 inverse on the left, I will get that G1 is in G2 times H. So this is the notation, and you should be very careful with it, because sometimes people tend to operate with this GH as elements, but this is just a notation for a set. So this is it is equivalence relation class, equivalence class, and so this is a set of all elements. So I can say that this GH is a set of all elements equivalent to H, so it's a set of all products, G times some element in H. Okay, so these are left, and then of course there is another definition. So what about right cosets? Right cosets, and let's do that as well. So of course here we will do HG. In the other order, it will be for notation. And here, so what else can we do? So we want it now to be H times G. So here notation will be H times G for the right coset. And here, so definitely I should do something different. So why don't I just do G2, G1 inverse? So G2, G1 inverse is in H. And no, it will be a completely different equivalence relation, but it is also an equivalence relation, as one can easily see. So, this is basically the definition. And so my group got partitioned into these classes called cosets. Okay, let's prove a few facts about them. Okay, so let me start with some examples. So example number 1. So our favorite example, let's take S3. So to make this example reasonable, I need also to add a subgroup, and the subgroup will be just a set of two permutations, identity and 2, 3. Okay, so let me also draw the standard picture we have here. So we have a triangle with vertices 1, 2, 3, and then so identity and 2, 3. 2, 3 is a symmetry reflecting our triangle. Okay, so and then the idea is that all my permutations, so there are 6 of them, can be partitioned into 3 cosets. So one of them will be, of course, our group itself, E23. And I'm looking at left cosets here. And next, I can see what happens if I take, for instance, an element, let's say 1, 3. So I need to multiply it on identity, and I need to multiply it on 2, 3. And if I do that, I will get 2, 3 times 1, 3. And, oh, sorry, I said on the other side. So I take 1, 3 times 2, 3. And this is a permutation which sends 1 to, so it will be a cycle sending 1 to 3, 3 to 2, 2 to 1. Okay, so it's here. And then if I take something else, for instance, 2, 3, 1, 3, 1, 2, then if I multiply 1, 2 on to 3, I will hopefully get the last cycle. And indeed, 1 goes to 2, and 2 goes to 3, 3 goes to 1, so I get here cycle 1 to 3. Okay, so and actually there is a very nice interpretation of what these cosets are. So these are permutations. So sigma of 1 equals to 1. If you have a permutation which sends 1 to 1, it will be one of those two. So these two permutations are permutations which send 1 to 3. So sigma 1 equals to 3. And these are permutations sending 1 to 2. Sigma 1 equal to 2. And in general, so if you take Sn and if you take a subgroup H, and this will be sigma in Sn such that sigma of 1 equals to 1. So this is a subgroup, and the subgroup clearly is isomorphic to Sn minus 1, just because you can take a permutation sending 1 to 1, it permutes the remaining n minus 1 elements, and you get this isomorphism. And then you can look at cosets. And actually cosets are just in bijection, so in 1-to-1 correspondence with elements 1 to n. And so your Sn group is partitioned into classes. Sigma of 1 equals to 1. This is the subgroup itself, it's H. And then you can look at sigma of 1 equals to 2, and so on, up to sigma of 1 equals to n. And this is really easy to see why these things are actually cosets. Because imagine you take this permutation sigma somewhere in one of them, and you multiply it from the right on a permutation which fixes 1. So if tau of 1 was equal to 1, then sigma of 1, of course, equals to sigma of tau of 1. And so if this was in one coset, then sigma tau will be in the same coset. And from here you can basically see that this is exactly the coset structure. So you can think of it in a slightly more poetic way, saying that basically if you look at this particular group Sn and the subgroup Sn-1, you can reconstruct the set on which it acted, the set you permute, as a set of cosets. And we will make this idea very precise in about a week. We will or maybe a little bit later, we will discuss what's called actions of groups on sets, and you will see how, if S3, for instance, is a group of symmetries of a triangle, you can basically reconstruct a triangle inside S3. You can explain abstractly, okay, there are some subgroups, and if you there are 3 of them, which are this subgroups of size 2, and basically you can think of them as vertices of your your triangle, and then they are connected by side when they are contained somewhere, and so on. So there is a way to kind of reconstruct these objects on which group acts from groups themselves, and we will see that later on. For now, it's just an example of cosets. Okay, so maybe let me give another example of a coset. So let's take, another example number 2. Let's take a group being G equal to real numbers. And this is a group by addition. So we just add them. And H will be a group of integers. And again, it's just a subgroup where we just add them. So there are these 2 groups. And of course, integers are inside reals. And so one can look at cosets. So what are cosets? So cosets, let's just draw this picture. So we have this real line, and we have 0, 1, 2, and so on. And let's suppose we take some point here, some element of G. And let's suppose it's, say, square root of 2. Over 2. And then, so what is a coset? It's some subset of G containing of this element, basically shifted using H. So in the same coset, we'll have element 1 plus square root of 2 over 2. In the same coset, we will have square root of 2 over 2 minus 1, and so on. Just all of them form a coset. So coset are integers, real numbers, but 2 real numbers are equivalent if they differ by 1. And there is a very nice way to picture it. So basically, if you just take this 0.0, 1 semi-closed interval, then these points are in bijection with all cosets. So 0, 1 is in bijection, just 1-to-1 correspondence with our Z cosets. And actually it's easy to see, so since R is abelian, left and right cosets are not different, they are the same sets. But there is something funny here. So if you think about it topologically, of course it looks weird, because in our bijection here, you know, if 2 points are close, they will correspond to kind of sets which are close, except if you take 0 and kind of point close to 1, they should correspond to the same set, because, I mean, we identify 0 and 1. So it is much more correct way of thinking to imagining cosets forming a circle. So by circle, I just take the 0, 1 numbers and I just put them on the circle. So this is 0, this is 1/2, this is 1/4, this is 3/4, and this is kind of almost close to 1, and then 1 is the same as 0. And so circle is parameterizing in this way nicely cosets. You can think of it, if you want, you can rescale it, think of it as 2 pi, and then it will be a very standard parameterization of a circle by radians. So actually points of a circle are in bijection with this cosets R relative to Z. And that's a very fundamental idea. If you, now you can think, okay, topologically, this gives a way of adding points of a circle, simply because, I mean, you can add real numbers, and it's easy to see that if you, if 2 numbers will be different by integer, you can add them, you will still get numbers different by integer. So actually what happens is that this set of cosets has a group structure given by addition, and it means circle has a group structure given by addition, and indeed it is just addition of angles modulo 2 pi. So that's maybe a very important example. We will see it later on again. So set of cosets relative to subgroup tend to be something interesting geometrically, and you can think of it as vertices of triangle in this example, or points of a circle in that example. Okay, so next I want to talk about some properties of cosets.